Today I'll be talking about toppling in a rigid body. Toppling in rigid body. For this, I assume that you know the three Newton's laws of motion. Okay, so in case of Newton's laws of motion, the main aspect is that we neglect the dimensions of object in case of Newton's laws. Okay, so if I say a block of mass m is kept on a frictionless surface and I apply a force F on it. As we neglect the dimensions of object, we can say that the center of mass is particle itself. Okay, so when I apply a force F on this particle, on this block, which is actually considered to be a point particle, I'll get acceleration is equal to F upon m. I use the Newton's second law of motion. We should always keep in mind that this acceleration is nothing but the acceleration of center of mass. But as the dimensions are neglected, the center of mass is the particle itself, and so acceleration is nothing but acceleration of center of mass itself. Now I'll give an overview of torque, which is going to be essential in our further discussion. So torque is a vector quantity defined as R cross F, where R is nothing but the vector starting from point about which torque is to be calculated, and joining the point of application of force. We know by vector product as R F sin theta is nothing but R cross F. So example, if I have point particle, I apply a force F to it. I want to calculate torque about point P. So I draw vector R, direction is pointing this. I extend the line of action of force. If this angle is theta, I can say that torque is equal to Rf sin theta. You can see that if I draw perpendicular over here, this is 180 minus theta, so this becomes R sin 180 minus theta, which is equal to R sin theta. So if I clump these two terms together, I get F times R sin theta. So we can define torque as perpendicular distance. This is perpendicular distance to line of action of force. Action of force from point about which torque is to be calculated. Now, talking about rigid body, we cannot neglect dimensions. As we cannot neglect the dimensions, the point of application of force, point of application of force matters. So we will get different result for different point of application of force. So consider a cube. Suppose this is a cube of height h of mass capital M. This is the center of mass C of the cube. It is kept on a frictionless surface. Talking about the forces acting on it, we will have mg pointing downwards. Suppose a force F is applied, which is at height A above the center of mass. Now, as suppose the block has only horizontal motion, now we know by Newton's laws of motion, summation Fy needs to be 0, where this is x direction, this is y direction. Therefore, there has to be a force which is nothing but the normal force acting. So we will get mg is equal to n. There is a reason why I am not pointing out normal over here. The reason is, now talking about the torque about the center of mass, we can say that this perpendicular distance is a. This is the line of action of force. We can say that torque about center of mass is nothing but F into A. Okay. Now, so as there is net torque on the object, it has the tendency to topple in the clockwise direction. But if the block doesn't topple in the clockwise direction, there has to be another force due to which there is a torque in anti-clockwise direction. This force is nothing but the normal itself. So we should bear in mind that in rigid dynamics, normal doesn't always pass through the center of mass. Now, for the object to be under equilibrium, rotational equilibrium, there has to be a torque in counterclockwise direction. Therefore, torque, the normal force shifts rightwards from the line of center of mass, or from vertical line of center of mass, or here. Now, suppose the distance is x. For rotational equilibrium, we write summation torque is equal to 0. Therefore, F times A is nothing but if this direction is this much, like this length is x, this is n, then we will write F is equal to Fa is equal to n into x. Okay, so we will get from here that F into A upon n is nothing but x. Now we want to know the maximum force which can be applied so that the block doesn't topple. Okay, bear in mind that as there is net force in the horizontal direction according to Newton's laws of motion, this block will always move with an acceleration where F is equal to m into acceleration of center of mass. So the center of mass will accelerate in the horizontal direction with acceleration F upon capital M. Okay. Now we want to know the minimum force, maximum force which can be applied so the block doesn't topple. We'll say that this x has some limiting value. This x cannot extend, as this is a cube, this is nothing but h by 2. So x cannot be greater than h by 2. Therefore x is always smaller than h by 2, implies Fa upon mg, where I substituted n from here as mg over here. So is h by 2. Therefore F is smaller than or equal to mg h upon 2a. Therefore, if this force is applied, this much force is applied, if this much force or smaller than this force is applied, then the block won't topple. If force bigger than this is applied, the block will topple. Now we should understand how the point of application of force matters over here. Now if the force is applied, instead of force being applied height A above the center of mass, if it is applied along the center of mass, on the line of center of mass, the torque about center of mass will be 0, and that is why normal will then pass through the center of mass itself. So the case will be something like this. This is center of mass, apply a force, normal will pass through the center of mass, mg will pass through the center of mass. There will be no torque acting on the object, and the cube will move with acceleration F upon m again. Now if the force is applied at a distance a below the center of mass, then the cube will have a tendency to topple in anti-clockwise direction. So if the block doesn't topple, then the normal has to be shifted to left side of the center of mass, from the line of center of mass. So thus we come to know that in rigid body dynamics we cannot neglect the dimensions of the bridge, and that is why the point of application of force matters, and the condition of equilibrium is net torque should be 0 and normal doesn't always pass through the center of mass. I hope you learned something new. Thank you for watching.